in geometry. So a direction and a size. And we have operations that you can do on vectors that respect the geometry. Those operations are dot product and cross product. Putting this together, we can ask, are there derivative rules when we apply derivatives to vector value functions with operations on vectors? So like adding vectors, scalar multiplication, subtracting vectors, dot product of vectors, and cross product of vectors. And the answer is yeah, there are. All of the properties are sort of derived from the fact that your vector components are just regular functions. And so if you do derivatives of regular functions, you have things like the product rule and the scalar multiple rule and the addition or sum rules. And so when you try to determine what should be the derivative rules for vector valued functions, you really just break it down to what's happening to the vector components and then take the derivative and see what does that look like when you're done. But intuitively, they pretty much work the same as the regular derivative rules. When it comes to multiplying a scalar times a vector valued function, you can either multiply the scalar first, then take the derivative, or you could take the derivative and then multiply the scalar after. Basically, you could factor out the scalar like you would with the regular derivative rule. Similarly, adding or subtracting vector valued functions, you can either do that first, then take the derivative, or you could take the derivatives and then add or subtract after. Once again, that's like distributing the derivative to each of the sum components. When you get to a scalar function times a vector valued function, that's going to be the same derivative rule as the product rule. Notice that you have the derivative of the scalar times the vector valued function plus the scalar function times the derivative of the vector valued function. When you get to the new operation of the dot product, turns out it's just the dot product version of the product rule for derivatives. So you have a dot product between these two vector value functions. That means you're going to get a scalar when you're done. But basically, you're just multiplying the x components times the x components, the y components times the y components, and so on. You could either do that first and then take the derivative, or you could take the derivative of the first function, dot it with the second vector value function, plus the first function dot the derivative of the second vector value function. Cross product is also basically just the product rule, except now you replace the multiplication symbol with the cross product symbol. Composition rule still makes sense. If you put a scalar or rescalaring or parameterization for your vector valued function, then it's just the chain rule. You take the derivative of the inside times the derivative of the outside. It just so happens the outside function is a vector and the inside function is just a scalar. There's an interesting property that says that for your vector value functions, these functions may not be constant vector valued functions. But if you take the dot product, if they give you a constant on the outside, then it is true that the derivative of this expression should equal 0. That is, the derivative of this dot product over here and the derivative of the other side of the equal sign would be equal 0. If you can take the derivatives of both sides of your equation and you keep equality. But that mathematically breaks down just to saying that, well, in this particular case, the dot product of the vector valued function and its tangent vector is guaranteed to be equal to 0. That is, the tangent vector has to be perpendicular to the original vector, at least if their product, dot product, equals a constant for any time t. In this section, when you're asked to use these derivative properties for vector valued functions, it just means start using the theorems to answer the questions. I want to show you what that looks like, what I'm expecting from you. So in the case of an exam or a test, you know what I'm looking for. So for this problem, we have a cross product of two vector valued functions, and we're trying to take the derivative of the result. The property says that it's basically the product rule, except instead of the regular multiplication, use cross product. So I should take I should take the derivative of the first vector, and then eventually cross it with the second vector. I should add that to the cross product of the first vector and with the derivative of the second vector. So do the derivative of the second vector first, then take the cross product. I can now take the cross product of these two vectors. The first cross product gives me this following vector. The second cross product gives me this vector. And the sum of those two cross product vectors gives me this resulting vector over here. Notice if I would have taken the cross product first and then the derivative, I would have gotten the same answer. In truth, you usually use these properties in the future to show that something is generally true. So this other example is just letting you determine something special about the properties of so this example is just showing you how to use properties to show that something's generally true. The way you prove things in math is you usually know what your goal is. So in this case, you want to show that the derivative of the cross product of a vector and its derivative is going to be equal to the zero vector as long as the above assumption is held true. So we start with the assumption that a vector valued function and its second derivative, the cross product of it, equals 0. What you want to show is that if you take the cross product of the vector valued function and its derivative, then take the derivative, you get a 0 vector. We don't know that's true yet, so we're going to use the properties to just find another way of writing this expression. So the product rule for the cross product rule for the derivative for vector valued functions is you take the derivative of the first, cross it with the second, then take the first, cross it with the derivative of the second, add the result. Now, the cross product works by saying that if you cross a vector with itself, or parallel vectors are always going to equal 0. That's because the magnitude of the cross product formula, generally speaking, is equal to the sine of the angle. The magnitude of each vector is equal to the sine of the angle between those two vectors. If those vectors are parallel, the sine of the angle between them is either 180 degrees or 0. In which case sine of 180 degrees or pi is 0, or sine of 0 is 0, so would be 0. That means that this particular vector, because you're crossing with itself, has to equal 0, or the 0 vector. Then the second part, which is not very much, is that we use the assumption that if you take the cross product of a vector and its second derivative, that's also going to give you the 0 vector. What you're left with is that the right-hand side of this equation has to equal the 0 vector from all your previous computations, and the left-hand side is just what we started with. We've now shown that the derivative of a vector and it's crossed with its tangent vector is going to equal the 0 vector, as long as we know that the vector value function crossed with the second derivative is also the 0 function, 0 derivative, 0 vector.